Start recording and start up our lecture. Does anybody have any questions before we get started? Fantastic. Okay. So this right here is what we were stopped on last time. We had been talking about which one's going to be the major product here and why that's the major product. And of course, it has to do with this right here, which is your intermediate, right? And so your intermediate, the more stable the intermediate is, the lower the energy the intermediate is, right? If the intermediate's lower energy, then you have less of a barrier to get to, okay? It's kind of like if, why do you go to floors 1, 2, and then 3 in that order whenever you come to floor 3? Well, because it's too much energy to get to floor 3 directly, right? Okay? And so, if you can go to a lower energy in between, you can go faster, right? You tried to go directly to floor 2, it would take you a long time to deal with that. Yeah. And this, why is that more stable? Well, that's what we were just talking about before, isn't it? Okay. This right here is a primary carbocation. This one is a secondary carbocation, isn't it? And so that one's quite a bit more stable, lower energy. Okay. Any questions? One of the things I would like to note here is in terms of thermodynamics, there's actually not a lot of difference, but which one's actually more thermodynamically favorable? The minor product, right? The minor product is, in fact, more thermodynamically favorable. Why doesn't that one end up being more then? I know, we're kind of doing a review right now. Irreversible reaction, right? These energy barriers are too large, and so going backwards is very difficult to do, right? And so, if you were able to make this a reversible reaction, this right here would give you the thermodynamic product, right? This product right here, being the major product, is the kinetic product, isn't it? Okay. And that's because of the speed of the reaction. Okay. So, Markovnikov's rule. Russian chemist Vladimir Markovnikov studied these reactions extensively. His rule, specifically as he stated it, was the addition of a hydrogen halide to an alkene favors the product in which the proton adds to the alkene carbon that is initially bonded to the greater number of hydrogen atoms. So an easier way to remember this, hydrogen goes with hydrogens. The other part, the halide in this case, goes with the more substituted side, right? The more carbons. This is the regioselectivity that's called the Markovnikov addition. It was more broadly applied because there's a large number of reactions that will give you the same sort of product for the same reasons. And so Markovnikov's rule is going to be something you'll see on a lot of these reactions. All it means is hydrogen goes with hydrogen. Okay? And then the carbocation ended up on the more substituted side, of course, because of what we just talked about. And that ended up giving you the second thing that added it. Okay? Could be an OH, it could be a bromide. Markovnikov, it would have been a halide of some sort. But this can be expanded. Predict the major product when endene is treated with HCl. So what's going to be the major product for this? So make sure you commit. You got to commit to some answer, okay? I didn't know if you understood the material. Interesting side note to this is endene right here in industry. You make Cameron endene resin, in fact. And anybody ever wondered what the coating on citrus fruits and apples is? It makes them very shiny looking and preserves them longer. That's what that is. Okay. So There you go. Okay. And so, which one's going to undergo this electrophilic addition? That's the first thing we have to figure out. Is it going to be the benzene ones or the... Nope. It's going to be this one, isn't it? Yep. Can't be the aromatic ring. Okay. And so these would be the two possible additions we could have seen, right? Okay, we could add the hydrogen on this side, in which case we get this one. We could add the hydrogen on the other side, which would give us the carbocation here. Okay, so what we need to consider here for which one's going to be our major product is which one has the more stable carbocation. Okay? And so we have secondary in both places, right? That doesn't help us. But this one is next to a double bond, isn't it? And so remember, those are delocalized electrons. When you have a pi bond next to it, they're going to be able to get pulled over into that carbocation, and they're going to stabilize that, aren't they? Okay? Just like when you have wealthy relatives or, relatives and friends that care about you enough and have a little bit of money. If you happen to have a huge hole in your finances, you can borrow a few dollars from them, right? I know. I am getting all sorts of creative with my examples now, aren't I? Okay? I'm trying to do less ones that are like... trying to do... Yes. Yes. Less violent ones at the very least. Okay. Yeah. Yeah, you like to... Okay. Okay. I'll still keep some. Oh, okay. Okay. So I will keep a mix of 30-70 violence. Okay. Okay, so again, that's going to be a Markovnikov's rule. It's similar. It's going to be one where it's stabilized you the carbocation. No, you're right. Thermodynamically, this is more stable. But kinetically, this is more stable. Yeah. And so because we don't have a reversible reaction in this case, where it's just a very large energy reaction, this is always going to end up being what's faster, not what's more stable at the end. Is that making more sense? And so it's more about what is going to give us the lowest energy intermediate, because that gives us the faster reaction. Okay? Kind of like if I was trying to hand out exams, right, it's actually faster for me to hand you directly the exam, right? It takes a lot more time for me to get people to pass the exams, right? Why don't I do that? Like stability-wise, that would be the most stable thing, right? That would give me the best results at the end, everything else. And why do none of your teachers do that? Well, we can't fit our fat butts between the desks, right? And so we pass them out at the ends of the deals. You all take a while to shuffle them over, right? And so it takes longer overall. And it ends up being a less stable solution. But what ends up happening is it's a matter of how fast I can actually do this. It would actually take me much longer to try to go through the rows, right? I have to try to through. That was bad. Better thing is just it is purely a function of how fast this reaction can go. This state right here is stable enough that it can stay together long enough to get this chloride back on. Okay? This one is going to be less stable, and so it's going to struggle to be able to get that chloride back on there. Okay? Mm-hmm. Mm-hmm. Near a carbocation? Yes. If you remember your order of stability for the carbocations, conjugation basically is like having another metal. Okay? So it counts the same sort of thing as if it was a tertiary instead of a secondary. So basically, this would be similar to an energy to a tertiary carbocation. This one would be more is secondary carbocation. Help you out there. Did that make more sense? Okay. So let's talk again about carbocation rearrangements. You all may remember the carbocation rearrangements from before. There's the hydride and methyl shifts, right? And they're the 1,2 hydride, 1,2 methyl shifts. Okay. And these are going to happen anytime that you have a carbocation that could be in a more stable arrangement if one of those things happen. Okay. And they're going to be typically faster than you getting a chloride back on there. You getting some other group to attack it. That's going to take longer. Okay. It's kind of like if you had a pencil to loan her and I had a pencil to loan you, who's going to be the fastest one? Yeah, you're definitely winning. And so, okay. Okay. So, there's the other arrangements, the minor products. So you could have the chloride here and the hydrogen here. Mhm. Well, that one not particularly, but this is going to be the major, the next product. Okay, so this right here, you're going to make that carbocation right here, right? And that would be a secondary carbocation. Well, a secondary carbocation is less stable than a tertiary, right? And so what can happen here is this has a hydrogen, and this can do what's called a hydride shift, right? And so if you were just going to say the Markovnikov addition product, you would have thought this was the major product right here, and you would have been, this is the major product. And you're not necessarily wrong, because it is the same amount. But when these products come out at the end, you start doing melting points and trying to figure out what you have here, you're going to be really surprised that you have something else that's the exact same amount, right? And so remember that when you generate carbocations, when you have high energy species, right, that you're dealing with, they're high energy. And so they can fall in all sorts of stuff if it's possible, right? It's kind of like, why don't you just like dance around on the peak of a roof? Because you can fall into all sorts of trouble, can't you? Because you're high energy. Okay. This is a high energy arrangement right here. And so if it can relax into a lower energy state, i.e. do a 1,2 hydride shift, which is shifting this hydrogen over here, then it's going to give the carbocation right there, which is a tertiary arrangement, right? And so this is, in fact, a lower energy state. And so that would be the more stable arrangement. Okay. And that would give you this product right here. Okay. So interestingly enough, if you attacked on this side with the hydrogen, you can't do a rearrangement because there's nothing else on the side. Or rather, if you rearrange, it would be the Markovnikov. So this is, again, the electrophilic addition we had talked about. And then we have a 1,2 hydride shift for our next step here. And this is just the coordination that we did before. It's the same amounts in this case. We're making the more stable one right here. Right here. That's the more stable one, which is the tertiary carbocation. This right here is the most stable carbocation. That's the one for the one we just did right here. Kinetically, it's going to be the most favorable because you're going to break up your energy states. This one. This one's the most favorable kinetic product. The only thing that's happening here, this has a lot of other things going into it that gives about the same amount of product here. So again, remember, you're splitting up your steps here. Okay, you have an additional step here. So you actually make the Markovnikov product first in terms of the carbocation. This is that Markovnikov product. If we had this chloride attack here, this would give the Markovnikov product. Okay, it's not the most stable carbocation you can get though. So you get a 1,2 hydride shift that pulls the hydride to hydrogen right here. And that gives you this other product, which is where the chloride goes on the tertiary carbocation, right here. So if we had this finish the reaction with chloride, that gives us this product here. This product is the 1,2 hydride shift. And there's kind of an interesting thing here that the anti-Markovnikov is what you call the other product, but not the Markovnikov product. And interestingly enough, you can have hydride shifts from the anti-Markovnikov product to the Markovnikov product, in case you're ever wondering. So it is something that can be done. All right. Let's try it on here. So detailed mechanism. Start drawing a detailed mechanism. And then predict the major product for this reaction. Gotta commit to it. Draw out that mechanism. If you want some paper. Yeah, I figured it died or you forgot it. Wanted to. So remember, complete that first step. You got your carbocation, high energy species, energy intermediate. And then look around it. Can you rearrange to give you a more stable carbocation? Okay. If you can't, then go for the Markovnikov product, right? If you can, then you need to accomplish your 1,2 hydride shift. And there's then a 1,2 methyl shift, it might be, right? What do I have there? Okay, I'm going to go ahead and move forward because we can only have so much time. So. All right. So the first thing you need to do is which carbon will the hydrogen attach to? And so it would be the one that gives you that more stable carbocation, right? Which is this one right here for the hydrogen attaching to. This is the secondary carbocation. Okay. So once we have the electrophilic addition portion, we have our carbocation. We look at both sides of it and go, is there a more stable? Can I do a 1,2 methyl? To get more stable, can I do a 1,2 hydride? Okay. If you have the choice of both, which one do you select? Hydride. Hydrogen's lighter, it's going to move faster, right? And so you would select the hydride. If you don't have the choice of both, you select the one you have. All right. So this side doesn't give me a more stable carbocation, does it? This side, ooh, I can move that methyl, couldn't I? Get carbocation right there. 1,2 methyl shift, that'll give me a more stable carbocation. And so that's going to be our rearrangement then. We'll have a 1,2 methyl shift. And so the electrons, by the way, this is that same inductive effect that makes these carbocations more stable. It's the exact same reason. You have your p orbital that's empty and it has positive charge. It's pulling on the electrons for those methyl groups. And so if it can rearrange to be more stable, it'll literally just pull the whole dang bond over. That's why it's called a methyl shift. It literally shifts the whole methyl group with its bond. Okay? And so, all right, we get our tertiary carbocation. Now we have the tertiary carbocation. We're then going to finish up our mechanism with our attack, aren't we? We'll get a nice attack here for a coordination bond. Okay, does everybody know why it's a coordination bond? Yeah. So all the electrons come from one species. That's why that's called a coordination bond. Okay, so the 2 electrons come from the bromide. You can do it with anything. For example, an H plus going on to an amine. That's a coordination bond. Okay. So depending on the symmetry of your product, the stereochemistry may not be an issue. So remember that if everything's asymmetric, we don't really have to consider that, right? However, if we have a symmetric environment, we will very likely end up with a symmetric product, right? Not always, but we need to start considering. Okay. So right here we have the diphenyl ethene, and this is going to have a single tetrahedral stereocenter. It's going to be formed, and the products are going to be chiral, in fact, because we can add from the top or bottom, and because we're going to have 4 different things around this center here, this is going to generate a chiral center, isn't it? Okay. And so how many things do you need around a center again? 4. Yeah. If you have 4 different things around a center, you very likely are going to generate a chiral center, right? You have to have a very, very unique circumstances not to. Okay. Everybody knows that I hate presenting laws as inviolable things that you can't violate, right? Because, like, it's happened 4 times in the last 2 years for organic chemistry. Which is pretty awesome, actually. It means there's a lot of really great scientific development, but also means I'm like, can you find exceptions? Probably. Do I want you to find exceptions? Yes. And send me that dang publication so we can put it up on the wall out here, okay? Okay. So again, this would be another example. In this case, this is actually a symmetric reactant, right? But because we're adding 2 different things in this reaction, it's actually pretty easy to generate asymmetric products, ones that will have chiral centers, actually, okay? Because, again, we're adding a H on one side, right, and a chloride on the other, okay? The hydrogen doesn't generate as many chiral centers usually. The chloride or the halide is the one that usually does it, okay? But if you have all methyls around a group, then yeah, the hydrogen's going to generate one. This will, in fact, typically give you a racemic mixture, where you have the hydrogen on one side and the hydrogen on the other side. Okay? So you can attack from above or below. So this is, again, the electrophilic addition. You're going to make your carbocation. Then remember that carbocation can be attacked from above or below. It's going to typically end up attacking so that you have the RS configurations are going to be generated here. And then you're going to attack from the other side. And again, because that's planar, you can generate both the R and S configurations. Okay? And so you will, in fact, get a pretty dizzying variety, if you don't control for any other variables, of products from these reactions. Okay? If you're chirality matters for your product, like you're making something that's going to go into biological systems, then this can actually be really annoying to work up and get your final product from. Okay, because every time you do these reactions, you can generate like 4 different products, right? So imagine if you do that a few times. You're gonna have to sit there purifying 4 different things. You all remember from lab, is purifying stuff something you necessarily will have to do a lot? Probably not. Okay, so let's talk about weak acids adding across this bond. We have here our bond, of course. We have water, which is like the stereotypical weak acid, right? It's actually the cutoff for weak acids. And we get no reaction. And you're probably not very surprised about this because you've probably had this mixture before in some way, shape, or form. You've had something with a double bond. It's in a water environment, right? Yeah. Now, what if we add a little bit of acid in there? A nice dilute acid, right? Yeah, we can get this reaction to go, can't we? Because what we need is we need to generate the carbocation, don't we? Once we generate the carbocation, water is a nucleophile. It's not a bad nucleophile. So this will work in this reaction. Now, the cool thing about this is, here, I'll go to the reaction so you can see it. Okay, so let's do this reaction. I'm going to have you actually come up with the cool thing about this. Okay? Let's look at this. So whenever we have acid and water, what do we actually have? We don't have the acid anymore. The strong acid's dissociated. That's gone. Okay? What we have is hydronium, don't we? And so hydronium is going to donate its proton. That is a strong acid, by the way. It's the cutoff of strong acids. Okay? Everything more acidic than hydronium is strong acid. Okay? And then hydronium is the strong acid in water. Okay, and so the H plus is going to attack. That's going to give us our Markovnikov orientation, right? And so we're going to have this carbocation right here. Super high energy species. We don't have to have good reactants past this point, do we? Carbocation is going to take care of all our energy needs. Okay, kind of like in biological systems, phosphate groups take care of all your energy needs. Add a phosphate. It's like the biological equivalent of carbocation. Okay. And so at this point now, we just need a nucleophile. It doesn't have to be a great nucleophile. Okay? Anything will work. Water, because it's a solvent here, is in really, really high concentration, right? And so that's going to be the one that's going to do almost all of our reactions, 99%. Okay? And so we're going to attack there with water. Notice that gives you the H2O plus, right? Because charges don't just change, do they? If you have a positive charge here, and you don't have any negative charges added in somehow, then you have a positive charge on the next side, don't you? Okay, and you keep having it until you remove the positive charge somehow. Okay? Now, that means that we have that H2O plus that's bonded there. Okay? There's only 2 things that can do it. It's high energy, right? Remember our cardinal rules? That's one of the largest additions of energy. Is we have to remove that positive charge. And so that means this hydrogen's very acidic, isn't it? And we have lots of water in there. And so the next step is going to be a proton transfer. We're going to kick that hydrogen out. That will leave us an alcohol. And that's going to give us H3O plus. What do you notice is kind of the nice thing? How much acid do I have to add to do this? Do I need a high concentration of acid for this reaction? No. Why don't I need a lot of acid to do this reaction? It regenerates. What do we call that if it regenerates? Catalyst. That's a catalyst. So it's an acid catalyzed reaction. Okay? You actually, in fact, only need like drops of acid for like a milliliter. Okay? And so it's quite nice, actually. Your major reactants are water here. This is actually a very common, this is very similar to acetylene, in case you're wondering. So pretty common gas that you can find, and you can just bubble it through acidic water, and then it's just water. So, with a little acid in it. The acid regenerates. So add a little bit more water if you start running low, but there you go. Yeah. So very, very effective reaction, right? And those are incredibly effective reactions. Actually, you see quite a bit of industrial use, of course. So HCI is not used to catalyze the hydration of an alkene in some reactions. Why don't we use HCl to catalyze these reactions typically? The chloride is a pretty good nucleophile, right? And so our problem is that we tend to get like the chloride adding to things, and we don't really want that product. Okay, so if we use the HCl, HBRs, we have a tendency to make those halides. Okay, they're just pretty small in comparison to like a huge sulfate group, right? And relatively light compared to a sulfate group, and yeah. Mm-hmm. At the end. Yeah, we just don't see it because it just adds to the two that are already there. Normally, you don't bother drawing out the H's. Your textbook does it because it's trying to teach you the reaction. This is styrene, by the way. In case you're wondering, it's the monomer for like styrofoam. Yeah. Okay. And let's look at another one of these reactions. So this is going to be the alkyne with hydrogen halide. This is actually going to produce what's called a geminal dihalide. You may remember your geminal dihalides and geminal groups. Nope. Okay. That's fair. So this will give us our major product, a geminal halide. Both of the halogen atoms are going to end up on the exact same carbon, which is what geminal means. Like Gemini, twin, right? Born on the same day. Okay. Geminal, born on the same carbon, right? Okay. This does take a little while. It becomes a little bit slower on the next reaction. And why does this say excess here? Why would you need excess? If you had a 1-to-1 ratio, just do it once, right? And you wouldn't get the full addition across the double bonds, the pi bonds. And so that's going to give us 82%. Do remember that we can have the anti-Markovnikov product on these things, and so we do get some of that. Not a huge amount, though. Okay. This is actually this reaction in terms of the mechanism. So again, we get that same attack that you're used to. This is really just the same reaction twice. And so you're going to get the carbocation. The chloride is going to add to that. And then we're going to have that around the double bond, right? And so then we're going to do that again to the double bond because it's still a pi bond. Okay. And that's going to give us our carbocation. That's still the more stable spot, even though the chlorides are technically electronegative, so they might withdraw some electrons. They have a lot of lone pairs that can donate into double bonds temporarily. Okay. So they actually do resonance stabilize that to some degree. Okay. They do, however, make this slower in many ways. Okay. That's why this does take a day to do. Most of these other reactions have taken like an hour max when we looked at them. This typically is a bit slower of a reaction. And so this is going to have, again, the most stable carbocation right there. That's the resonance structure, by the way, where you donate one of the lone pairs into a double bond from that chloride. It's that same resonance structure you may recognize from like the carbonyls with oxygen. Okay. Okay. And so that's going to give us then that geminal dihalide. Okay. Does everybody understand what geminal dihalide means? Geminal to di to halide. And so if it's chloride, you do chloride, bromide, bromide. Okay. Now let's look at it without resonance stabilization. What happens there? Well, it becomes much longer of a reaction. You have to do a lot more time. to make up for that. Okay. So here's HBr. And again, we're going to get this reaction. It actually goes to 100%. But this is going to take 4 days. And so one of the things that happens here, and this is kind of interesting, is you can actually form what's called a pi complex with the H plus, with that pi bond. Okay. If you're interested in learning about more interesting and weird things that can happen, come join me in inorganic chemistry. Okay. We'll actually learn about complexing there. But this is actually part of this mechanism right here, is that it's actually going to have this H plus come in here, and it's first going to join a complex, okay? And then what it's going to do then is when this comes along and interrupts that balance there, that energy balance, this is actually going to give its electrons here and allow the electrons to release onto the hydrogen, and then allow these to come up. It still ends up being the same Markovnikov product, because again, it's still more stable to have positive charge here. This is going to have more positive charge. Okay. But it's actually kind of an interesting dynamic where it actually forms a complex first. Okay. So it actually would look, in terms of the energy diagram, if you were to like calculate this, a little different than you might think. Okay. All right. So in case you're wondering, this is propyne. Anybody know anything about propyne? It's it can be used as like rocket fuel, and it's been heavily researched in that field. Okay, so this right here is going to be an acid catalyzed hydration of an alkyne. This is going to produce a ketone in this case, and this is kind of an interesting portion of this, because you may have went, oh, shouldn't I get a di-alcohol? Because that would be like the dihalide, right? But you got to remember, there's going to be part of that reaction that we're going to have a unique, interesting resonance structure. Okay? And you'll recognize it in just a minute. So again, this is going to be an acid catalyzed with water, and then we're going to get a ketone at 90%. Okay, so the mechanism, it's the same mechanism you're familiar with for the first part. So we have the hydrogen coming on. This gives us the more stable carbocation. And then we have the H2O coming on here. This is going to give us that H2O plus, right? That's a very acidic proton there. And so that's going to come off on a proton transfer. And that leaves us with the alcohol, right? But this is where your memory is going to start maybe firing a little bit from last semester and going, enol. I've heard of enol somewhere, but hey, that didn't seem very stable, right? We didn't get a lot of enol products coming out of things. And that's because enols typically are not very stable, because they can do resonance structures. They can tautomerize, okay? And so what's going to happen here is this is actually going to tautomerize and give you the carbonyl instead, because you generated that enol here, okay? And so remember, you can have acid or base tautomerization. We're already under acidic environment, right? And so this is going to be an acid catalyzed tautomerization, okay? In case you're wondering, very, very common reaction in biochemistry, okay? Very common. You will see that a lot. So if you keep your eyes out in biochemistry, okay? And it may not get pointed out, but you can go, oh, tautomerization. Oh, that's the enol again. They set up the enol. The enol's ready. Okay? They're going to change it. They're going to modify it. It's going to go to an iso now because the damn enol was made. Okay. Okay. And so this is going to give you the carbonyl. In this case, it's going to be the keto form that's the more stable, because that would be the Markovnikov addition form, right? If we were the aldehyde, that would have been the anti-Markovnikov. Okay. Okay. Now, the yield of an acid catalyzed hydration can be increased by using a Bronsted acid catalyst stronger than sulfuric acid. You may go, oh my God, that sounds dangerous. And yes, it can be dangerous. But remember, you're only using catalyst amounts. So you only have to have a few drops in there. So it's not as dangerous in that case, right? Now, this again is that same reaction. If we use this acid system right here, this is a whole system that you have to use. You can't just do this in like normal solvents with everything else. It has to be set up. You can use this catalytic trifluoromethane sulfonic acid is what that is. And that is an acid that is stronger than sulfuric acid, and it is going to fall apart completely in a very spectacular manner. Do not try to take a bath in that. Okay. This would give you an even better yield. Okay. It will allow you to push this reaction to essential completion. Okay. Now let's talk about doing this with like a conjugated double bonds. So remember, if you have a conjugated double bond here, then this is going to have some resonance structures available, right? If you make a carbocation here, well, that double bond can give its electron density and form a double bond here instead, right? Which would give you the carbocation here. Okay? Did everybody understand that okay? Or did I lose people? Some of you look like, okay. So remember, I'm going to draw carbocation right there, right? So that would be your first form, right? When you see that form, hopefully your mind goes, okay? And you go delocalized electrons next to a carbocation, right? That means they're going to get pulled over, okay? And so you go done and done. Right? Everybody kind of see that now? Okay. And so what is this overall, these two Heckel structures tell us is the overall resonance structure? Positives on two, right? Okay. And so we'd have these partial positive charges on those two. Okay. That means when the chloride comes along, what are the choices? Yeah, we can pack up. Yeah. And so we can get two different structures. Okay. And we'll get some of each. All right. Notice that double bond. It's not in the same place as the original structure, is it? And that's that dang resonance structure. We had a little bit of a rearrangement there, didn't we? And so these would be our two structures here. And again, this would be called the 1-2 addition when it goes right here, because it's the 1-2, right? The 1-2 doesn't necessarily have to be the first and second carbons in that structure. It just means they're next to each other. The hydrogen and the chloride are right next to each other, just like the 1,2 methyl 1,2 hydride. Just means they're next to each other. Then the 1,4 addition would be the other one. 1,4 meaning that we skipped. Okay. And so we had the 1 here. We had the 1, right? Because we have the hydrogen. Okay. And then that's 2, 3. And so 2. Okay. So again, remember that does not matter what the actual numbering is. Okay? It's just telling you the difference between those. So if you start counting on that hydrogen one, if you want to do a 1,4, you go 1, 2, 3, 4. Now you put your chloride. Okay. All right. This is what that mechanism looks like again. So here we have the hydrogen coming on again. We generate the carbocation. But because we have delocalized electrons that can form resonance structures, we actually are going to form that resonance structure, right? And then this is with everything, the resonance hybrid structure. with the proper terminology, I've used the deltas here. And so that means we have this positive charge on both of those spots, right? And so this chloride can attack either one of those spots, and that would give us the 1,2 product and the 1,4 product here. Okay. The exact amounts can vary of what you're going to get for this. So usually pretty even-ish. It's not like 10% versus 90% usually, but you can set up situations where it will be. But depending on what you have substituted there, it can give more positive charge in one place, less positive charge. Okay, so you can modify this. All right. So, what about where we have this right here, and we have the anti-Markovnikov when we first do this? So what happens if we have the anti-Markovnikov addition? What would that do? We get no resonance, right? That's not a resonance. You need the delocalized electron next to the carbocation, don't you? And so that can't skip over here. That'd be like me having you give a pencil to you. Apparently you need the pencils today. Everybody at the end of class. Pencils, sir. Okay. No. There are carbocations. Again, that conjugation, resonance stabilization of the carbocation intermediate is going to drive your reaction mechanism. So remember, your Markovnikov product would have been the most stable in the first place, because this would be more stable, right? And so that's going to be the majority of it anyways. Can you get some of the anti-Markovnikov? Maybe a little, okay? But it's going to be very, very low because you have this nice resonance structure you're competing against, okay? This is going to be favored tremendously. So at high temperatures, electrophilic addition to the conjugate diene is reversible if we have high enough temperatures, and that's because we can overcome our energy barrier on the reverse direction, right? And so for a reversible reaction, what controls our amounts of the product? Thermodynamic product, right? The lower energy product, okay? At low temperatures, this is going to be irreversible. If we're an irreversible reaction, then what controls our product? Kinetics, right? This part controls our product, okay? So irreversible, your energy barrier controls your products. The energy of the intermediates controls your products. Reversible reactions, like high temperature conditions, then it's the energy of the product, the final product, that controls the reaction, okay? The barrier doesn't matter because you can go back and forth over and over. Okay. Again, which one makes it so that the thermodynamic product is favored? High or low temperatures? High temperatures, yeah. Which one makes it so the kinetic product? Low temperatures. Okay. Thermodynamic product of the electrophilic addition to a conjugate diene is generally going to be one in which the remaining CC bond is the most highly stable alkyl substituted form. That typically gives you the most energy for your final product. And so, for example, this one's a monosubstituted alkene. This one right here is a disubstituted alkene. And so this one's going to be the more stable form, right? If you remember your alkene stabilities. The more stable alkene is the one that's more substituted. So at high temperatures, which one's favored again? This one, right? Yeah. Okay. So at warmer temperatures, that one's the favored one. Now notice that did it make it so that it's 99%? No, it didn't. Okay. Typically, it's not going to do that. In fact, you probably can't get high enough temperatures to push something, and it wouldn't even matter at a point. You'd actually cap. Okay? It's not like higher temperatures will favor this more. Okay? Unless there's some difference in terms of... Typically, cool temperatures are going to be things like ice temperatures, and it will say not room temperature usually. Okay. Okay. uh, so this would be cool temperatures. You'll typically see them being negative temperatures. Okay. Uh, and typically, these sort of questions, you can just put warm temperature, cool temperature, that sort of stuff. Okay. So this right here, negative 80. Anybody know how you get a negative 80, by the way? Is that ice bath? Definitely not an ice bath, is it? So what you typically use is like an organic solvent like hexane, and you put liquid nitrogen in hexane, and that will give you ice baths for whatever the melting point is. Okay, ice baths, they're being frozen solid organic substance baths. They're usually called slush. Okay, and you can maintain that negative temperature that way. Okay, so this is the 1,2 abductor right here. This is going to be your kinetic product, and that's because the chloride is actually located after completion of the first step of your mechanism, and so it is literally the faster one to get to. Okay, I know, that's quite nice, isn't it? It's literal kinetic, like you would for driving a car. Okay, and so you can get to this one faster. This one takes more time to get over there. And so that, of course, is the one that forms faster. Does everybody remember retrosynthesis? This is the retrosynthetic. This is the on-do reactions, meaning you're looking at the reaction in reverse. So if you're planning a target, you'd start with a target, a thing that you want to make, right? And then you'd have to plan the reactions backwards to figure out what starting products you want. And that's called retro, backwards synthesis, right? Okay. And so this is going to be the on-do addition of the HBr, right? And so we have an HBr across something and we undo it. Notice you don't always know where your H is. Where is your H here? Well, here, because these were benzenes, right? But they can actually be either way, and then you have to go, which one would have been the Marconi code? Okay? So be aware and be careful. Right. This would be an alcohol ether here. Both could actually give you the same sort of thing. You could have done R instead of alcohol in the previous cases that we did. And this would be the on-do addition of the H2O or the methanol, ethanol, the alcohol. And again, that would show you that double bond. That would be the reactant you'd use to get this product, right? Okay, this is the geminal dihalide. And so what would your reactant be? Well, we would undo the geminal halide. And remember, the hydrogens goes with the ones with more hydrogen, right? So it's that side. And so our triple bond is over there. This is the ketone one right here. There's the ketone. And again, that has to have been the hydrogen, doesn't it? Okay. And so that right there is our triple bond. When you're drawing these things out, one of the things that please keep in mind, if you have a double bond, it branches. That, right? If you have a triple bond, it does not branch. Triple bond. Okay. And so I have been noticing people have kind of gotten lazy on that. You may not want to get lazy on that because it actually matters in a lot of cases for geometry and stuff. And so it's just better to keep your mind actively following those patterns. Okay. Okay. And so this right here would be the allylic halide where we have the double bond and the halide on there. And that would be that conjugated system we were talking about. See, the double bond ends up in the middle, doesn't it? And so the double bonds will be on both sides of that. Okay? All right. So how can you carry out the following synthesis? I need you to draw out that retrosynthesis for me. How can you carry out this synthesis? Oh, wow, we're doing great on time, actually. You guys understanding this pretty well? No? Oh, okay. You're so quiet. And you're not super expressive either, so I guess that's the 8 o'clock difference. If you don't understand it, please come office hours. There's other ways I could have explained things, and then working problems will help a little bit too. Okay, so remember the retrocensus, you're always going to take your target, right? And it's going to be the one that you're going to end up with, right? And so that's going to be the one with the cyanide is going to be your target, right? And then you're going to do these hollow arrows, which mean the retro or reverse, okay? That we're doing an undo. You start with the cyanide. And then what we're going to do is we're going to undo a variety of reactions, which will get us back to that bromide, right? Okay. Okay. And so what bond do we have to make here? Yeah. We have to undo that substitution and undo putting that CN on, right? Got to get rid of that CC bond for the CN. Okay. And so this is going to be an undo. The easiest reaction that's probably most in most of your minds, it would be a substitution, like a nice SN2 or something, right? SN1, SN2 reactions. Okay. The exact one we're using here doesn't really matter, to be honest, because there's not a lot of rearrangements and other stuff we have to deal with. So it's a benzene ring. It's pretty stable. So undo substitution, right? I don't care which. We don't have to specify yet. And so we have a bromide here. That's a good leaving group. Does the bromide have anything to do with bromide here? No, not really. Okay. It's just convenient. And it is nice if you're going to have a bromide or a chloride that you maintain bromide and chloride so you don't have all these different halides everywhere. And you screw things up. Get chloride on there by accident. But bromide's just a very good leaving group, right? And so we have our undo substitution that would leave us with this right here. That would have been our intermediate that we may have purified and left for a day or two, and we came back to it, right? Okay, and so we have the bromide species. How can we get into the next thing? Okay, what would be a good way to generate? Well, we know that we have elimination reactions, right? Elimination reactions would be the next nice step, right? So we can do an undo addition. So we're going to use eliminations and additions to go back and forth for these next steps. Okay? And so this is going to be an undo addition this time, meaning that we had done addition, right? And that will give us the double bond here. Okay? And we use HBr there, which is quite nice because it's related to what we've been talking about. Okay, so how would have we generated that double bond? Well, we would have to do an undo elimination, right? We would have had to do elimination to make the double bond, okay? Which is where we tie in with the chapter we just did, right? Is we have additions that we talking about. This right here is the undo elimination, of course, from last semester, eliminations. And that would be where we have the bromide at the beginning, which would have been our initial thing I gave you, reactant. And this is the entire reaction altogether. So we just take this synthetic pathway we've now done in reverse. We just flip everything. We put normal arrows now, and the species we need to add for each. Okay? And the reason we do it this way is because do I know what reactant I want to use when I'm trying to figure this out? Do I want to have to consider 20 different reactants while I'm trying to trace this out? No. No, it's just like when you make a paper, you put an outline first, right? You get kind of a loose idea of what you want. Okay? We're getting our loose idea here. And then we fill it in, right? With the more specific strokes. Okay. Do I want to specify on my shopping list? I want the Kirkland brand of this and that, or do I want to look for the one that has the best price? Ooh. I want the best price, best quality, right? Kirkland brand is actually pretty good. Admittedly. Probably a bad example. Do I want the great value brand? Tougher. Also usually pretty good, but okay, so that's our final synthetic pathway. Did that make sense for everybody? Okay. Don't forget to practice, because in the heat of the moment, it makes sense. Later on, it may not. Now, many natural products are in fact terpenes or terpenoids. This can include things like steroids, of course. Everybody knows steroids, right? Yep. Hopefully not super familiar with steroids. But this can also be essential oils from plants. It's actually a whole variety of products. It can be sealants, etc. Okay, there's actually a tremendous variety. This right here is an isoprene unit. So when we're looking at terpene or terpenoid, this is going to consist of repeating isoprene units. They'll be linked together by terminal carbons of those isoprene units. So for example, this is an isoprene right here that's ready to do a reaction to make a terpene. Okay? And so what do you notice about these double bonds? Oh my goodness, it looks like the stuff we've just been talking about, right? Which is why this is it. This is without the double bonds being expressed, because that's just the basic isoprene unit. This would be a complete isoprene unit with the double bonds. They can be in different locations. Yeah. So this right here is actually a terpene. This is a monoterpene in this case, and this is alpha-penene. This is limonene right here. You may notice and recognize some of these. Anybody know what limonene is? Yeah, it's the smell of lemons, and a lot of what you experience from like lemons and citrus fruits is limonene. And so this is another, of course, terpene. And right here we have a diterpene right here. That's cambrine. So penene, that sounds a lot like pine, doesn't it? Anybody want to guess what that one is? Yeah, it's the pine resin. A lot of the smell comes from that. There's little undertones that are not that, but you know. Anybody want to try to guess that one? No, unfortunately not. The name doesn't have a lot to do with it. Anybody had ginger? Yeah, this is ginger oil. Okay. Unless you've actually done actual ginger, you probably haven't really experienced that much. There's not a huge amount of ginger oil in the ground up ginger. That's why it's a little bit. Anybody ever cut like actual ginger root up and pressed it and stuff? Yeah, it's pretty different than bottled ginger at the grocery store. Man, I love fresh ginger. The last one. Anybody want to try the last one? This one's really unique. It's isolated from certain corals. This one's a much more unique, weird one. Okay. Cool. So squalene, that was a precursor to lanistanol. That's actually what all steroids are derived from. And again, this is another terpene that we're talking about. This right here is the number of pairs of isoprene units. So for a monoterpene, it has one pair. That means two of those isoprene units. So for a cisquesterterpene, it's going to have one pair. This is going to give us 3 in this case isoprene units. We don't have an additional pair, and so we can't have a higher number there. This one right here, 2, and that'll give us 4 individual units, right? And this one, 3, 6 individual units. Mm-hmm. Mm-hmm. These are these. The 5 carbons in that arrangement. And so for the reactants that you would make these things out of, they would look something like this. They'd have different arrangements of double bonds around them. Okay. And typically when you make your final product, they're going to have some rearrangement of those double bonds around there. Is that making more sense? Yep. And those are those. If you ever look at your testosterone, all that, those sort of steroids, then you're gonna see that like you can actually see these laid out around it if you start really looking at estrogen, etc. Right? So it's actually quite fascinating. This is terpenoids right here. This is methanol, geraniol, retinol right here. You guys probably recognize many of those from like biology. This right here is, how am I doing for time? I am 2 minutes away. Yeah, I can finish this actually. So this is isopentyl diphosphate here. Okay, and that's the diphosphate group here. And so terpene biosynthesis is quite a common phenomenon. Oftentimes it's going to be first started with acetic acid that you actually start, and you start assembling these terpenes from. Okay, because acetic acid is quite a common group made in your body, actually. Anyways, this right here is going to be that same fundamental structure of a terpene, actually, in case you're wondering. This is actually how that starts right here. So right here, we're going to have the isopentyl diphosphate. Remember, this is going to be that same sort of structure we see. And this is going to be our enzyme. Notice what sort of reaction that is. That's that first addition step, isn't it? So we're taking that hydrogen, we're attacking, we're generating that carbocation, same as we did before, didn't we? The enzyme is actually going to help on the next step, and that's going to regenerate that catalyst by removing the hydrogen. And that's actually what's going to generate our double bond there. So we get this addition elimination steps. It's really similar to the reactions we were just doing with this, right? That's why we did the additions, we did the eliminations, additions, and now we can do addition elimination reactions. Oh my goodness. It's like you got a whole toolkit that can work together. I got you a nail, I got you a hammer. Go build stuff. Okay. Build entire organic systems. Make them mirror people. They're toxic to all life on the planet. Yes. Wipe us all out. Okay. Probably both the mirror people and us. Okay, so this is actually the synthesis of neryl diphosphate and geranyl diphosphate right here. And so these gives us our two different conformers of these. Does anybody have any questions about anything covered in the chapter? This is actually geraniol right here, which is like the smell of roses and stuff. It's a flower smell, of course. And this is a typical pathway to that right there. This is actually how they make limonene. You know how they make like the citrus smell and things? They do not extract that natural product. We would have to isolate way too much product and use way too much solvent, which would actually be horrible for the environment. So it's actually made synthetically. And this right here is the synthetic pathway. So if you want to make some citrus spray, there you go. Huh? Is it? Yeah. Here, let me see what you got here. I'm having trouble hearing you over